Okay, the last time we discussed the transmission line parameters. What are the parameters? Can anyone tell me what are the parameters? Without looking at your notes, what are the parameters? Just guess.
Conductors.
Conductance. أيوة. G. أيوة.
Resistance and inductance.
Inductance, very good. And
Capacitance.
And capacitance, of course. When we talk about inductance, therefore we talk about capacitance. Capacitance depends on the electric field. Inductance depends on magnetic field. So magnetic field, that creates inductance. So there is no physical inductor. There is, because we have magnetic field in the wires, in the transmission lines, therefore that will create inductance. Because we have electric field, therefore it will create capacitance. Because we have power loss, therefore will create resistance. Because we have leakage current, therefore we create conductance with G. So these are modeling. Okay, so when we model, that's why we use math. We use math to model the circuit. So in physical, we have transmission lines. But we modeled as transmission line parameters. So we modeled the transmission lines with the 4 parameters. So we talked about the electrical factors the last time, or the transmission line considerations. Okay, we have 4 electrical factors and then mechanical factors. Also, we talked about what are these. So you need to know these. Okay, if you're talking about the exam, of course, some short questions will be from here. Okay, what are the transmission line design considerations? Maybe give examples of an environmental factors, something like this. Okay, so environmental factors. What is it? Exposed to the population, the safety, the land values. Okay, the exposure to electric and magnetic fields. These are all environmental. Because exposure to electric magnetic field to animals, for example, there are some research about the effect of transmission line to animals. As you can, if you go to Europe or USA, you will see the transmission lines run through the farms there, through the farms. So there are animals also behind, close to the transmission lines. These are extra high voltage transmission lines. They are not distribution that is at your house, close to your house, that's okay. But those are extra high voltage, so they will have very high magnetic fields. And there are some research that the effect on these, on the animals. Yeah. Okay. So this is also environmental factors we take into consideration. So what we need to do when we design this, therefore we need to make it in to take all the necessary design components or criteria. Okay. We already talked about transmission lines, and we mentioned about the conductors. AAC, for example, what is ACSR? You will say aluminum conductor steel reinforced. So this is maybe a short question. What is ACSR? What is AAC in a conductor? AAC is all aluminum conductor. This is all aluminum alloy conductor. When we have A, we alloy, extra A. And then we talked about the phase conductors, the bundle conductors. When we have the the transmission line either per phase, now talking about per phase, either one line per phase or 2. This is a bundle conductor, 2 per phase, as we will show, and there are 3 or 4. Okay, and the spacing is the same now when we have more than 1 conductor per phase. More than 1 conductor per phase, we call bundle conductors. And these come at extra high voltage. You see now here when we reach 345 in Qatar, at 220 you will see 2 phase. At 220 you will see 2 conductor bundle. At 400 kV you will see a 2 conductor bundle. Why do we have conductor bundles? To carry more power. You need to carry more power because of the current. When we say power, you relate it to current. Okay, high current. Why? Because voltage times current. Even though we increase the voltage, the current is still high. Therefore, we can have a bundle conductors to carry more power. And also, it has other so many advantages of bundle conductors as we come to bundle when we talk about bundle conductors. It's not only to carry more power. There are other advantages also. So many advantages. But once we come to bundle conductors, for the time being, what you need to know is that we have, when we go up in the voltage, go higher voltage, then we convert into bundle conductors per phase. Okay. And then also we talked about the resistance and how to calculate the resistance. Okay, as if you increase the length, therefore the resistance will increase. If you increase the area, cross-sectional area, the resistance will decrease. And I relate to you the wire, the simple wiring system in your house, for example. If you are connecting an oven in the kitchen, for example, an oven, this will have about will have 6 millimeter. The size of the wire is thicker than connecting lights, for example. So the lights, the size of the wire will be 1.5 millimeter or 2 millimeter, while for AC will be 4 millimeter or 6 millimeter, and so on. So the area here to carry more power also, to carry high current, we increase the area to carry high current also, and this will also reduce the resistance. And then we relate the circular mill and the square mill. Okay, we said the circle mill, a circle area, for a circle area, because we deal with the transmission lines. These are circle transmission lines. The area is a circle area of the conductors. It's a d square, small d square. And the relationship we talked about, the relationship between d, small d square, when we talk about circular mill, and d square capital. This d square capital is the diameter also the same, but this d is in inches. Okay, inches square. And this one is circular mill. And the relationship is what? Is 1,000. So you multiply by 1,000 d square, but this is 1,000, and then because of d square, so 1,000 d times 1,000 d, therefore there you will see the square in here, and it will give you small d square. Okay. So this is in inches, the d is in inches, and this d, small d, is in mils. Now, they also, please note that the relationship between square mill and circular mill. We talk about area. Here we talk about square. So this is square mill and circular mill. The square is just pi over 4. Okay, so if we divide over pi over 4, you will get the circular mill. Okay, so either we do it as square mill or a circular mill. Both are areas. This is a square and this is circular. Okay, just pi over 4. Divide the relationship is pi over 4. And we've talked about the American wire gauge. And that's why actually when we mention about why we need to change to circular mill, because this will be very small, 0.0235 inches. So we want to convert it into mils, for example, mils. So this will be 25.35. Now, and then we mentioned about the conductivity. The conductivity, the reference of the conductivity is copper. Copper, we say for 100%. What's the one which is higher than copper? Is silver, not gold. Gold comes between silver and copper. It's better than aluminum. Aluminum here is 61%. So gold is higher than aluminum, maybe 75 or 76%. Okay, so it's between copper. So the most conductive material is silver, and then comes copper, and then gold, then aluminum. Okay, related. Okay, so we use gold for the corrosion, because it is resistant to corrosion. That's why we use gold. In electronics, you can see the wires there are made of gold, and it is easy to drawn there for the flexibility of the gold. Okay, so they can make it easy to draw the line instead of just having copper there. So it's easy to form a circuit board, for example, with gold. It's okay. So it goes easy. But remember, but copper is still higher than gold in conductivity. Okay, and gold stands because of the heat actually from the electronics. Therefore, gold can withstand the corrosion. It can withstand the weather and the heat for a long time. So we use gold. But in terms of, but why we use aluminum in overhead transmission lines? Anyone can tell me? Why do we use aluminum?
It's lightweight, that's why.
Very good. Yes, because it's light. We lose some losses here because of the conductivity is less than copper, and it's also cheaper than copper. So it's two reasons we use aluminum. It's cheaper, and it's also lighter than copper. Okay, this is the way when you design something. You have advantage, you have disadvantage. Okay, I will lose some power losses. Does it worth there to have copper there? And so on. Or silver, for example. Will I buy silver because it's a good conductor? Or aluminum? Okay, so this is what you do, compromise. Power losses is okay, 61% compared to copper. This is very good also. But if you look in iron, for example, it's only 17%. You see, very, very low iron. So we don't use iron, although it's a conductor, but it's very low conductivity. Okay, the table here, what is given, okay, and then we talked about the skin effect. What is skin effect? We reached here about the skin effect now. So the AC power is power loss over I square R. The AC, the resistance, what we talked about is DC resistance. And when we do AC, therefore, it depends on the frequency. So we take it like this, power losses over I square. This will give you what is the resistance. Now, skin effect, what is skin effect? You already had this in maybe electromagnetics or any other course, maybe any other course you took this skin effect. What course you have taken the skin effect? Besides electromagnetics. Electromagnetics, is that correct?
Yes.
Yes, besides electromagnetics, have you seen this skin effect?
Doctor, it wasn't in details. It's just it was a part of in the research about the effects of electromagnetics. So it was discussed there. It wasn't a part of the course.
Okay. So the
physics class discussed this.
In physics, okay, very good. Okay, very good. Okay, so skin effect, you're familiar with the skin effect, and the current distribution is non-uniform. And that's why I told you that you can have a pipe there, it's hollow from the middle, if it's solid. We can make it hollow. Because electricity, the current, the electrons inside in the middle there will be very, very low, but all crowded at the outer surface. So that's skin effects. At that power frequency, the AC resistance is a fewer percent than the DC resistance. You see, if we have a DC transmission line, there is no problem. It will be the solid. It will not have skin effect for a DC transmission line, but skin effect comes with the AC transmission. Okay. So the AC, because of the 50 hertz, so there will be few percent higher than the DC. So just to relate that, why we have resistance, because the electrons crowded at the outer surface. So we call the current crowded at the outer surface of the conductor. So therefore, the resistance will be higher a little bit than the DC. Okay, we mentioned about the relationship between the square and between square mill and circular mill. Please remember this. Now, what we want to do, this is an example in your textbook. Now, the picture here you see has nothing to do with the example here, but it's but just to show you what we mean by 19 strand. This is 4/0 American wire gauge, so AWG. So the type is 4/0 and 19. So we need to specify what these two, 4/0, 19 strand. This means it has 19 of these circles. 19. Okay. And this is okay. So that's what we, just to show you that what we mean by strand conductor. Okay, we call it stranded conductor, so it's made of strand. And this is also to reduce the skin effect. The part of it is to reduce the skin effect instead of a solid. Therefore, the current will flow on all these strands to make them smooth. So all the covers, all the transmission lines are like this. Okay, strand. Okay, let us look at the example here. We say table A3, this is an appendix 3. List 4/0 cover. You see now it gives you the type of what cover, what conductor it is, 4/0. Now think as an engineer, and this is what you will do as an engineer. You will be given tables, and you need to, from the tables you can read these tables and work on these tables. So this is the idea now, to focus on how to read the table. What table? We will come to the table. Okay, we want to read this. Come to the table. We want to read this. This table here. This is what will be given. Okay, this is in the appendix, table A3 in the appendix. Okay, how? This is an easy task, but an easy task and easy what to do there. But you need to know how to do it. Okay, so you're given this one, then you can determine here the other information that you can deduct from here. Okay. All right. So let us look at the example. Table A3, which is the one that you just showed. You see, 4/0 copper conductor with 12 strands. Strand diameter is 0.1328 inches. Let us look at this 4/0. I would like you to, this will be also in the exam, by the way. You will be given this table here. So you need to know how to search the information and solve the problem. Now, what it said that it has what 19? It has 4/0. So you look in here, American wire gauge. This is the, before we go in there, let us zoom in. Zoom in. Now, this is the size of conductor, so it's an American wire gauge. This is circular mills, and they are sorted from higher to lowest. Okay, it's 20,816, 510. So you are familiar now with circular mills. So they are sorted into according to the from highest to lowest of the size of the conductor. And then we have what's called the American wire gauge. The American wire gauge is gives this one here. 4 over 0, 19. Number of strands. You can see the number of strands. And then the diameter of individual strand. So for each strand, now you are familiar with strands. In inches, the diameter of each strand, not of the whole conductor. And then we call this outside diameter of inches. So this is the whole conductor. So we have strands and we have the whole conductor, the outside diameter. And the breaking strength, weight, the carrying capacity, current carrying capacity. So this is the capacity. You see now 1,300 for the conductor. You see, we're talking about thousands of their conductor. So 1,000 is the capacity here. We're talking about 500 ampere or 600 ampere for a conductor, one conductor. Geometric mean radius, and this we'll discuss this in chapter 5, GMR. And now here the resistance. This is our part here for this chapter. Is the resistance for this topic. We have DC. We have 25 hertz. We have 50. We have 60. As you can see here, the DC is 0.05, for example, for this conductor, 0.0585, and then 0.0594 as the frequency increases, 0.06, and then at 60, 0.0634. You see, from 50 to 60, there is an increase of resistance. Okay. Now, if the temperature increases, from 25 to 50, also the DC will increase, now 0.06, and the AC will also increase. So with the increase of temperature, it's 50 hertz. The resistance will increase. The reactance, this will be in chapter 5. We talk about this. So this table here will be with us in chapter 4, chapter 5. Okay. So now we want to determine so this is given, we want to determine the resistance. So what is given? We're given this only. 4 over 0, 19 strands. 4 over 0, we have 3 types of conductors. They're all model 4 over 0, American wire gauge. They're all model of these, American wire gauge. Okay. The American wire gauge gives 19. What do we want to find? We want to find this number here, although it's given in the table, but we want to verify this number. So we want to where this 211,600 circular mill comes from. It comes from these. So they already calculated for you. So we want to verify this number. So what we did, we go to the example here. Okay, verify the total copper cross-sectional area of this number in circular mill. So we want to verify the number there, which is written on the table. So the answer already is written there, and we want to calculate. How do we calculate this one? What is given? Given 12 strands, and the diameter is 0.1328 for each strand. Where do we get this 0.1328? We get it from the table, 0.1328. خليكم معنا حلوين. So we come here, where is it? Strand, we come here. It's not per strand, but it's by strand, outside diameter in inches.
Doctor, the third, the fourth column, 0.1328. It is under 19 strand, 12 strand, the fourth column. Here, yes, doctor. The diameter of individual strands.
The diameter of individual strands, yes. 0.3, where are you talking about this one?
Yes, 0.13. Yes, this one.
0.1328, very good. And for the 12, exactly. For the 12, I was looking for the 19, but the 19 is only the picture of 19. Has nothing to do, as I told you. So we are talking about 12, very good. Okay, so 0.1328. So this number here will not be given to you. So what we give you the type. For example, this 4 over 0, 12 strand. Then you will look here and find the diameter from here. And then you will go to use the formula sheet, your cheat sheet or formula sheet, you will be given this. What we want to find? We want to find this. So you will be given this one. Okay, so verify the cover. So what we have, pi over 4 d square mil, blah, blah. So what we do, area. Area equals 12 strands times d square. So this square is 132.8 square. 12 times 132.8 squared give you this circular mill. So we can have it as a circular mill. Okay, after we, of course, after we change it, this 0.1328, first of all, we change it into this number here, mils. Okay, now remember d or d square. This is d, diameter. So therefore will be mils, not square mils, not circular mill. Okay, if it's d square, then it will be circular mill. But this is length. So are in mils. Okay, area is in square mils. All right, so that's the what you will do here. 0.3128 inches, which is given on the table inches. Just multiply by 1,000, give you in mils. And what we do with these mils, we just square. This is for each strand, and then how many strands we have? 12. Therefore, we get this number. So you verify your answer. حلوين? Okay, which agrees with table A3. Straightforward. So this is good. The second part of it, what we want to verify, the DC resistance at 50 hertz of 0.302 ohm per mile. We talk about per mile because this is an American textbook, so we use miles. Assume 2% increase in resistance due to spiraling. Okay, 2% increase. What's spiraling? Spiraling is the spiral like this, what you see here on the picture of the cable. It's not straight, it's spiraling. Therefore, the length increase because this is spiral. And therefore, what length? There is about 2% increase of the length. Therefore, what we will do here, we use this formula. What do we want to find? We want to find the resistivity at 50 hertz. Given the resistivity at 25. So the table here, again, the table that what you see is only gives us this resistivity. Therefore, we want to find at 50 degrees. It's not on the table, therefore we need to find it. Okay. How to find it? We use this formula here, this model. Okay, so the resistivity at the second temperature, the first temperature. The first temperature which is given is 25, is 10 point, the resistivity 10.66 from here. Ohm circular mil per feet, this one. Okay, copper, 10.66 to find from here. T2 is the new temperature, which is 50. Plus T constant. So this is 241. Where do we find it? From here. Temperature constant, 241.5. And also we add it for this, for the denominator. T1 is the 20. At what temperature? 20 degrees. This one, as you can see, 20. Therefore, you will add it. Okay, please do not cancel this 241.5. You will say 241.5 and you cancel with this. These are not multiplication, this is addition. So you should not cancel, you just add it here, add it here. If you cancel these two, 50 over 20 will give you 2.5. But that's not the answer. Okay, so please don't cancel 2.5. But that's not the answer. And please do not tell me stories there with that I forgot to add 241.5. I forgot, I just canceled them, I just made a simple mistake, because this is straightforward. But as an engineer, those mistakes are not allowed. Are not allowed. Okay? It's not simple mistake. This is our fatal mistakes that we don't know. You're just plugging in the numbers because this will be given to you. So what you are going to do? So the idea here is to test your focus, not to plug in the numbers. So please note this. So in these type of questions, you cannot do any. Well, you cannot actually say that I forgot to add temperature or I cancel them. I canceled the 241.5 over 241.5. It's a small mistake. What's a small mistake? Because there is nothing actually else to grade you on. Here we'll grade you that are you working as an engineer or you're just writing any numbers and then you will submit it to your manager. So you will be given things like these to work out. So there is no room for mistakes. Okay, حلوين. Now we treat you as engineers. To be treated as there is no room for mistakes. These are already given. We give you the formula sheet, we give you the table. So what else now you can do? There's no focus. It means you are just plugging in the numbers. So you will be very hard in grading when you do mistakes like this. It's already given now. So you want the new 10.66, you will go to 10.66. So we took this hard drawn copper. Hard drawn copper and annealed copper, you can see the difference. Annealed copper, this is the way they about the temperature, how they draw the copper. And the hard drawn is the way that they take the wires from, how they make the size of the wire. It's called hard drawn. Okay, so 10.66 is from here. Circular mill per feet. Circular mill per feet. So this here, by the way, these temperature constants you may be asked here. These sometimes we use them for the models. So we want to find, this is what modeling is. This is the beauty of math. You do modeling in here, and then you found yourself we need to add an offset, to add some numbers in there. Then we call it a constant. Okay? So to balance the model. Therefore, our model becomes is right. So our models simplifies the reality. Okay, so these equations simplify the reality or simulate the reality. Okay, that's why you will see constants. Constants is to balance the formula. Okay, the model. All right, so so we got this Ohm per circular meter feet, and then what we do here, we want to find RDC. Now, what we want to find? We want to find only this is the length 5280, and we multiply it by 2%. Added not for stranded. You need to change this for spiraling. I mean spiraling, not stranded. Spiraling. So we added 2%. How do we know? It's given. So it's about 2%. The length increased, and the length is given here 528 miles. 5280. 11.88, which is the resistivity. So this is over the area. So this is rho over the area, which is this part here. RDC at temperature 50. Rho times length over area. And this area now we're talking about circular mill. So we put the circular mill area in the denominator. And this is in miles. We add it in miles, so okay, 1.02. So 2% extra. Just add. And this is the resistivity 11.88 circular mill per feet. Okay. All right.
Doctor, we determined the length 5280 from the table, or it's given in the question?
No, this must be given. Must be given in this one. Table entries for capacitance conductor diameter is with for this conductor verify spiraling to percent increase in the resistance due to spiraling. 5280 is where is it now? Okay, 5280 exactly 5280 because it's not written here. 5280 will be standard for all, I guess. Whereas will be this one here, ohms per mile. So per mile, 5280 per mile. So this is feet. So we convert mile into feet. So that 520. So 1 mile equals 5280 feet. Okay. So this is per mile. Okay. So we convert the mile into feet. So this must be given to you, or from the table you can. You see now the focus now comes in. Thank you for asking this. Now you see that, and the table is given miles, but here is given in this table here is given circular mil per feet, and on the A3, the appendix table is given per mile. Therefore, you convert per mile into feet. Okay. If you can go back, how back I don't know. How back I will go. Okay. Anyhow, you convert the mile into feet. Not written here, but you can convert the miles into feet. All right. That's good. Good notes. So sometimes we give you these units, and you need to focus and to find what are given. Okay, so we'll not make it clear, straightforward for you. Now you teach you as an engineer. Engineer will be given only charts like this. Then you need to work. Okay. All right. Okay. So those written here, but because we're talking about per mile, even the area there we're talking about is all per mile. So which is per feet per mile. So we change it into we so multiply by the numbers 5280. Okay. All right, which agrees with table A3. Therefore, we got this, and it's still here now per mile. You see now we change it into per mile. What is it we given? So okay, so this will be per mile. 2116. Okay. All right. Okay. Now the last part on this part of it here table A3 from table A3. What's from table A3 is ADC at 50 hertz are these ones. So here just to show you that as we increase well, the AC is higher than the DC, the resistance. Okay, the AC resistance is higher than the DC resistance by 0.3%. Here is 0.7% for 25 degree. You see, for 50, 0.3%. At 25 degree, 0.7%. You will say maybe why it's 50? 50 because it comes hot. The temperature of the transmission line is hot. Okay, especially in summer will be even hot. Will be 50. 50 just outside temperature will be about 45, something like this. And then with the current there, it might come more than 55. That's the temperature of the conductor. Become even more, maybe 60 degrees or 55 degrees. All right. Okay, so that is that's clear. Here we are. Okay, for a conductor length of 1 mile, so it gives you here 5 to 8 feet. Okay, that's good. Or even the example already given to you. Okay, for 1 mile, this is 5 to 8 feet. All right, so we know now how to determine the area, to verify this area given only this part here, only one, 4/0 or 19 strands. So we know this is copper. And remember, this is copper A3. Appendix 4 is aluminum. That's another thing that we will do, but not here. This is we talk about copper, you go to appendix 3. We talk about aluminum, you go to appendix 4. Okay, table appendix 4. Aluminum. So this is in copper. See, so this is the only one that's given. 4/0 and strands of 19. All the rest then you can determine it. The area, the length, per feet, per mile, whatever is given. And please note here also what are here, the geometric mean distance. This is in feet, but that's later, inshallah, we'll talk about geometric mean distance. This is in chapter 5. The outer strands is in inches, not in feet, okay, in inches. So please make sure that you read the units, okay? So it's not just plugging in the numbers. The units are important, that we test your focus. Okay, these are you test your focus, that there is no room for mistakes. All right. The second part of it, this is only we zoom in, is the conductance. For the third part, so we talk about resistance. Now we conductance. So conductance, we talk about corona. Again, corona. What you already heard about in corona? Where? What? In what course you heard about corona? Not coronavirus. Talking about corona, the power loss, corona. Where? In what course?
I think a little bit about in electromagnetics, maybe.
Electromagnetics, yes. Electromagnetics, yes. So corona, what's it called? When there is electric field strength, so high value of electric field on the conductor causes the air to become ionized. This is the idea of corona. High value of electric field on the conductor surface, the air becomes ionized. What do you mean by ionized? Then you will see the air sparking there. You see the air and also the noise with the air. You see, okay, and you will see the sparking. You will see lahab. Okay, you will see there's lights, not lights, but sparks. Okay, ionization of air. Where is this we can find? We can find also through the insulators. The insulators on the transmission line that we discussed earlier, glass or porcelain. Also, they got dusty. They have dust on there. The dust decreases the conductivity or the insulation. Insulation, not conductivity. This is insulator. So the dust decreases the insulation. Therefore, or the rain, for example, you see rain there, water will also decrease. Although the rain will wash the dust, that's good. But also it will decrease the insulation. The dust is really one of the big factors that affects these insulators. Okay, in some insulators you will find them, they are wrapped, so they are protected from the environment, from the dust, protected. Okay, insulations are protected. You see there with the rubber, with the material there. Okay, so corona occurs when high electric field strength at a conductor causes air to become electron-ionized to conduct. So therefore, the conduction occurs. The real power loss, because there is a connection or conduction there, Then there's a real power loss. There's a current. So that's power loss through the insulator or through the conductor and another conductor. You will see this corona, okay, because of the air ionized, and you see them clearly at night. You see them at morning. You cannot see. Hard to see them, but still they are there. But you can hear also the noise like this if you are close to a transmission line. Okay, because of the leakage of corona. So usually it's compared to conductor loss, of course, these are small, but they cause interference also. Conductance usually neglected in power system studies. So when we do simulation, we neglect this if we're talking about corona loss. So corona loss is we can neglect the power loss itself. Any leakage current, that's power loss. That's why you will see the shunt admittance. We neglect the shunt admittance, but we never neglect the conductance. The conductance, the G, we can neglect it, the G. Okay. This is a very small component of shunt admittance. So, but the capacitance, we will not neglect it, we will be there. But G can be neglected, the shunt G. Okay, G is the conductance. So the R, which is connected between the conductor and ground, R. So okay. So sometimes now this is corona. If you want to know more about corona, visit this in your leisure time. This is a very interesting. It's by BBC. Where is BBC? I don't know where, but anyhow, but they do it by BBC anyhow. The very interesting video that you can watch on corona, and you will see them how they see corona and what they do. And it's really a very interesting thing to watch. When we talk about magnetic flux, we still have 2 minutes. When we talk about magnetic flux, we talk about what? Inductance. And we'll come to the inductance later. Now, inductance, to find inductance, what we do here, first of all, you need to know these terminologies. Important now because you are engineer and you deal with communication or so the flux density, the permeability, magnetic field intensity. H is magnetic field intensity. B is magnetic flux density. mu is the permeability, سماحية. Okay, so to find the inductance, what you do first, you need to find the magnetic field intensity, H. Then you will find magnetic flux. This is what, please read the textbook. Okay, how to find the inductance. Okay, so we start with magnetic field intensity. Then we find the magnetic flux density, B. And then we found from B, we find flux linkage, lambda, called flux linkage. And then we find the inductance. So when we talk about flux linkages, we talk about inductance. So from here to here to there. Okay, and we will, inshallah, come to this one. Please register for attendance before we go. Attendance here. Okay, so please register for attendance. So I stop here for the